Welcome dear students, welcome to today's online class. Today we start another module, that is solid state 2, which is a very short module dealing with some important properties of crystalline solids. In today's class we discuss the first one, that is defects in crystalline solids or solid state defects. We can also say imperfections in crystals. What does it mean? We know that crystalline solids are having periodic arrangement of particles and there is a regular repeating pattern. However, we will see that in most of the crystals there will be some irregularities in the arrangement of particles. That is known as defects in crystals. It is because we know, according to third law of thermodynamics, the entropy of a perfectly crystalline solid tends to zero only at 0 Kelvin. Perfect order is possible only at 0 Kelvin, and that is an unattainable temperature. And so at temperature, any temperature above 0 Kelvin, that is what is normally there will be some disorder in the crystal. So that is due to various reasons. Defects appear due to sometimes missing of some ions in the lattice, sometimes it may be due to misplacement, or it can be due to some impurity atoms present in the lattice, etc. And interestingly, it is that presence of impurities bring up some interesting properties to the crystals, like electrical, optical properties. Now, defects are classified in this way. First, into 3 types. Point defects, that is our discussion. We are concerned with point defects only in the syllabus, in which there will be missing or misplacement of ions in the crystal lattice, and this defect is limited to a particular part of the lattice, not extending over the lattice. Whereas line defect is the defect which spread over a one dimension axis along a line. That is one dimensional imperfection. Whereas plane defect is a defect which spread over a plane, a 2D imperfection, 2-dimensional defect. So point defect can be called a 0-dimensional defect. These defects are found at certain local points in the crystal lattice. Now, point defects are divided into 2 types broadly: stoichiometric defect and non-stoichiometric defect. What are the difference? What is the difference? You know, stoichiometry of a compound, the ratio of the ions shown by the formula. For example, if you write sodium chloride, we write NaCl. You know, this is not a molecular formula, this is only a formula unit indicating that Na plus and Cl minus ions are present in 1:1 ratio. So that's the stoichiometry of sodium chloride. If you check the crystal of crystal of sodium chloride, if you see that the number of ions are as in the formula, we say it is stoichiometric. Okay, there are some crystals which exhibit non-stoichiometry. Now, what is a stoichiometric defect? A defect which do not affect the stoichiometry of the compound. That means which doesn't violate the stoichiometry. Due to the defect, there is no change in the ratio of the ions as given in the formula. That's what. Now, non-stoichiometric defects are defects which disturb, which change the stoichiometry of the compound, or due to that defect the ratio of ions are not matching with the stoichiometric formula. Let us first discuss the two types of stoichiometric defects which we have to learn. Very important, that is Schottky defect as well as Fungal defect. What is Schottky defect? It is a point defect due to missing of ions. When ions are missing, it should be both anion and cation because stoichiometry is to be maintained. So, equal number of anions and cations are missing. So, when an ion is missing, that is known as vacancy. So, that is lattice vacancies will be created. So, in Schottky defect, there will be lattice vacancies, equal number of anion vacancy as well as cation vacancy. See, this is a simple representation of the lattice. This will be a negative anion, so this is anion vacancy, and here it is a missing of cation, so cation vacancy. That is Schottky defect. So defects due to missing of equal number of anions and cations in their respective lattice. Definitely due to missing of these ions, density of the crystal will decrease because there is missing of ion. So mass will be lost. So Schottky defect results in decrease in density. That's a striking difference between Schottky and Fungal defect. So the first point is here, it is missing of ion. We can put examples for Schottky defect. Compounds which show Schottky defect like sodium chloride, cesium chloride, silver chloride. These are examples for crystals showing Schottky defect. Another point is that here the crystals are having relatively high coordination number. So Schottky defect is shown by crystals having relatively high coordination number. And another point is that the size of anion and cation will be comparable, not much different. When they greatly differ, the defect will be mostly fungal defect. So just opposite almost. So these are 4 points related to Schottky defect. It is due to missing of ions, equal number of ions and cations, producing lattice vacancies, and it is common in crystals having high coordination number, and also anions and cations are having comparable size, and it results in decrease in density. As a rough estimate, a crystal will contain as many as 10 raised to 6 Schottky pairs per cc. That's the count. Coming to fungal defect. Here, it is that one of the ion, mostly cation, because cations are generally smaller in size. So the one of the ion is misplacement. It is misplaced into an interstitial site in spite of its respective lattice point. I repeat, in fungal defect, it is a defect in which an ion, usually cation, is present in an interstitial void in spite of its respective lattice point. That means, suppose here you can see this cation is supposed to be here. This may be one of the void, of course, we know. Suppose it is in tetrahedral void. Supposed to be in tetrahedral void, and it has moved to an octahedral void. Suppose that is misplacement. This is what is fungal defect. Misplacement of ion. Now, this misplaced ion is called interstitial. Okay, and it's very clear that in fungal defect there will be no change in density because it is only misplacement, no missing of ion. This can be called cation vacancy, and this is an interstitial. No change in density. Example for crystals showing fungal defect are zinc sulfide, right? You know, zinc is having much smaller size, so zinc ions will enter into the interstitial voids. Silver bromide, silver iodide, etc. And it's very important that silver bromide is showing both Schottky defect as well as fungal defect, HBr, right? So that's about Schottky defect. and Schottky and Fungal defect. See, these vacancies are important in solid state properties, because when there are vacancies, to this vacancy nearby ions can move, and that results in solid state conductivity, and due to what is called diffusion of ions, right? So diffusion of ions takes place due to these vacancies, and that will enhance the electrical properties. Okay, now we go to, and again here you can see this fungal defect is possible when ions are having much different size and coordination number is relatively less. We go to the next type, that is non-stoichiometric defect. See, as I said earlier, when the defect is non-stoichiometric, that means due to the defect there will be change in the stoichiometry or change in the ratio of the ions as given in the formula. It can happen in two ways. So this is again divided into two types. That is, one is metal excess defect. That means metal excess. See, this non-stoichiometry can happen due to either increasing the number of cation or decreasing the number of cations, or increasing the number of anion or decreasing number of anions. So one is metal excess defect, where cations are more than anions, and the other is metal deficiency defect, right? Metal deficiency defect. So there are two possibilities. Now this is again, let us first discuss this one, metal excess defect, which we can take two examples. One is metal excess defect in a specific crystal, that is that of zinc oxide. Zinc oxide is showing a metal excess defect, and the second one is what is found in alkali halides. Alkali halides are showing a kind of defect which results in what is called F centers. You will see that. Let's consider first of all the non-stoichiometric defect in zinc oxide or the metal excess defect. See, if you check in the lab, zinc oxide, if you heat it strongly, it will turn yellow. What is the reason? See, we are representing the lattice of zinc oxide. So it will contain Zn2 plus and O2 minus ions. We take zinc oxide and heat it strongly. What happens is that on heating zinc oxide strongly, it loses oxygen reversibly. It will dissociate like this. Zn2 plus is there. It will lose oxygen. So what happens? This O2 minus will get oxidized and form oxygen atom or molecule, and leaving out 2 electrons. So this is the dissociation. Oxygen becoming a gas will leave the lattice. It will go off. So what become excess? Zinc will be excess, and also electrons will be there too for electrical neutrality. So we can now show the ions Zn2 plus alternatively coming. Suppose this I am not showing here. Okay, of course, Zn2 plus and O2 minus coming alternatively. Okay. So this is a lattice of zinc oxide. Okay. Now, on due to this, oxygen has gone and there is excess Zn2 plus. What happens to this excess Zn2 plus? That will occupy that will occupy the interstitial void. See an excess, you can see an excess zinc ion in the interstitial site. So this excess zinc ion occupy one of the interstitial site, and this will be the electrical neutralities will be attained by some equal number of electrons which are trapped nearby. This 2 plus is balanced by these 2 electrons which is obtained from oxygen. Oxygen has left the lattice. So this is metal excess defect. So in short, there is excess cations in the lattice, and interesting part is that for electrical neutrality, electrons are trapped in the neighborhood. Now these electrons, these free electrons are responsible for this electrical conductivity and also the yellow color. So optical and electrical properties are enhanced due to this defect. So zinc oxide at high temperature will show enhanced electrical conductivity that can be explained by this defect. And also zinc oxide, which is originally colorless, on heating strongly will turn slightly yellow. So that color change is due to the presence of these free electrons. Now coming to the next one, that is the kind of defect found in alkali halides. See, this is obtained when you heat alkali halide in presence of alkali vapor. For example, suppose you are heating sodium chloride in an atmosphere of sodium. Sodium chloride crystal is heated in an atmosphere of sodium, it will show yellow color. If you take potassium chloride crystal and heat in an atmosphere of potassium, it will show lilac color. If you heat lithium chloride in an atmosphere of lithium vapor, you will get a pink color. So what is this color due to? This is due to the defect which appear in alkali halides on heating alkali halides in respective metal vapor. So let's see what is the kind of defect which appear here. We know that alkali halides are known for Schottky defect. So there might be a lot of Schottky pairs in the lattice. Let us consider, for example, KCl. So let me show the cations and anions, K plus and Cl minus in the lattice. And I am deliberately avoiding or showing one anion and one cation vacancy. So this is Cl minus. So this point is a cation vacancy. K plus is not seen. This is an anion vacancy because they are showing Schottky defect. Now, if this crystal is potassium chloride crystal is heated in an atmosphere of potassium vapor, excess of potassium vapor is there, what happens? At the high temperature, this potassium will ionize into K plus an electron, right? Because you know alkali metals are having low ionization enthalpy, so they ionize on the surface of the crystal, and these ions will diffuse down into the cation vacancy. So this K plus will enter here, right? And for electrical neutrality, this electron, the removed electron, will come and get occupied in the anion vacancy, right? And this is known as, this trapped electron is called F center. F comes from the German word Farb, meaning color. So color of this crystal in this experiment is due to the trapped electron here in the anion vacancy, right? So this color is explained due to the presence of this vacancy and trapped electron, and this is a kind of defect seen in alkali halides, that's called F center. In these two cases, you can see that Cations are coming excess. Here zinc is excess. Here K plus is excess, which is electrically balanced by the electron. Now the last one is metal deficiency defect. In metal deficiency defect also we have two examples, right? So this is over. Coming to metal deficiency defect. There are two examples here also. One is the defect found in non-stoichiometric compounds like FeO, right? Similarly, FeS, etc. Let us take for example FeO, ferrous oxide, iron 2 oxide. Even though we write FeO, strictly writing, we see that the formula is not stoichiometric. It is to be written here sometimes Fe.95, Fe.950. What does it mean? Actually the formula is FeO, supposed to be where the Fe2 plus and O2 minus ions are in the ratio 1:1. But in actual crystal, if we investigate, we see that the ratio is not 1:1. For if oxide is 1, this is only 0.95. That means what? There are some metal deficiency. Some Fe2 plus ions are missing in the lattice. So that is a kind of defect shown by FeO, such non-stoichiometric compounds. Let us represent the defect now. This kind of defect is shown by D block metal oxides, sulfides, etc., where D block metals are showing or they are able to have variable oxidation state. That's the reason. So what happens in the crystal lattice of ferrous oxide? Let us show the ions Fe2 plus, alternatively okay, these are Fe2 plus and oxide ions. So the crystal lattice is supposed to be like this, where you have equal number of anions and cations. But in actual practice, we see that some Fe2 plus are missing. It's not seen in the lattice. Fe2 plus ions are missing. That is leading to metal deficiency. But you may ask, then how the charge is balanced? Remembering Fe2 plus moving to Fe3 plus state. They get excited, they get transferred into higher oxidation state because that is possible, right? So 2 plus 2 positive charges are missing, so 2 Fe2 plus will move to Fe3 plus. Then only 2 positive charges are balanced, right? Now the charge is balanced. So this is what happens. So this is the kind of defect found in FeO. Some Fe2 plus ions are missing in the lattice and the charge is balanced by equal number of Fe2 plus moving into Fe3 plus state. So what is the advantage now? A lot of advantages. See, there's a cation vacancy. Ions can diffuse into these vacancies and cause ionic movement and kind of solid state conductivity. And again, since there is Fe3 plus and Fe2 plus nearby, electron can move from Fe2 plus to Fe3 plus. See, electron can move this way. And so that this become Fe2 plus and this become Fe3 plus. Electron can electron can move. Conduction of electron is possible because of having ions in two different oxidation states. So you will see interesting electrical property in this case also. Coming to the last one. The second metal deficiency defect appear. This is a very special case that's called impurity defect. Impurity defect. That is, sometimes we can add small amount of impurities to the crystal lattice and that can cause missing of cations, or metal deficiency can be created by adding small amount of some impurities into the lattice. Example is, if we are adding strontium chloride is added to the crystal lattice of sodium chloride. This is an example. Another is cadmium chloride can be added to silver chloride crystal. In these cases, impurities enter the lattice and that results in cation vacancy. Let us explain this example. A small amount of strontium chloride is added to sodium chloride. What happens? Let's see. Whenever you have to explain defects, you should have a drawing. You should represent using this kind of sketch. That's very important. Let us show them. We are showing sodium chloride lattice, so Na plus and Cl minus. Okay, these are Na plus and we have Cl minus. This is the lattice, crystal lattice of sodium chloride. Of course, this will have Schottky pairs, Schottky defects, of course. Now, which we have not seen, shown for convenience, what we are doing, a little amount of strontium chloride is added. The point is that strontium ion and sodium ions are having comparable size. So, strontium ion, strontium is Sr2 plus. It is a dipositive because second group, right? This is a monopositive. So, strontium ion substitutionally enter the lattice. That means strontium ion will replace sodium ion in its place. That's what happens. That's called substitutional solid solution. So, in place of a sodium ion, we are writing strontium ion. Okay. So, we have incorporated impurity ion. So, this is an impurity, a foreign atom, correct? A foreign atom. It has entered the lattice substitutionally. So what happens now? There is an extra positive charge due to Sr2 plus. So it's to be balanced. For that, what happens is that one Na plus will leave the lattice now. One positive charge is reduced now. So addition of one Sr2 plus is producing a cation vacancy. That is the net result. That is what is a metal deficiency. This is called a metal deficiency defect, because the host cation is missing, right? Again, this is producing vacancies that will cause ionic diffusion and that can result in electrical conductivity. So these are various types of defects found in crystals. Thank you.